Okay, so this time we're going to take a break from work itself, at least in our understanding of it with physics. And instead we're going to take a look at conservation of energy, one of the new things that we've been dealing with. We're going to use it to get a better understanding of amusement parks, roller coasters to be precise. So I've got a situation where I've got a roller coaster that goes up with a really big hill initially, may have a loop. Maybe, actually let's do one more little hill back over here. Looks like fun. I've got a car up here at the top. And it starts off there. It's actually pulled up, usually by a chain of some kind, that does work and puts energy into our system. We're not going to look at that though. It starts off up here at some height, h naught, our starting point. I'm going to say that it has an initial velocity equal to 0 meters per second. And this is going to be our position 0. In other words, our very beginning position. What I want to know is how fast is it going down here at a different point? Basically when it gets to the bottom of the first hill. How fast is it going down there? It is at some height, 1, which is going to be equal to 0 meters. It'll have some velocity, v1, and that's what I want to know. And finally, I'll tell you that up here at the top of this, my initial height equals 15 meters. That's about, what, 4.5 stories tall, about 45 feet, more or less. Okay? So, what I'm going to do is I'm going to apply energy on this. I'm going to take a look at the energy I start off with, energy naught, versus the energy that I end with, my final energy, E sub 1 over there. Well, what type of energies do I have? We're looking at a point right up here when all the work has been done by that chain, so we don't really need to worry about that. One way to try and figure out what energies you're dealing with are ask yourself what forces are going to act on it. Well, one of the main ones is going to be gravity. So we're probably going to have some potential energy due to gravity. So I have an initial potential energy due to gravity. Okay. And I'm going to be dealing with something that's moving, so I'm likely to have some kinetic energy. So this is my initial one. We're not really dealing with any springs, no magnets or anything like that. So for the most part, these are probably the only forces that we're going to be dealing with. We are going to ignore air resistance. And friction. It's not entirely realistic, but it helps to model a system simply first to get an understanding. We could always go back in and find the work done by friction and actually adjust for that. But for now, we're going to find out, hey, if we ignore those things, how fast would we be going? Okay. So in light of that, these are probably the only types of energy I have. This is a pretty common setup for most of the initial mechanics problems. And so over here, at the end, my second point, when I'm down at the bottom there, I've got some potential energy due to gravity, plus some kinetic energy. All right. Well, since I don't have any non-conservative forces like friction or air resistance working on it, this should qualify under conservation of energy. So, remember that conservation means that what you start with, you end with. That gives us a relationship where E naught equals E1. Okay, well let's see what we've got for each of the energies. E naught, potential energy due to gravity, that's mg h naught, plus, kinetic energy initial is going to be 1/2 mv naught squared. Over here, by the same token, I'm going to have E1 is going to be equal to mg h1 plus 1/2 mv1 squared. And I want to find v1 so I know how fast they're going. Okay, well if I start plugging in values, my initial velocity, v naught, is actually 0, so that goes to 0. And another value that I have that's 0 is h1. This guy goes to 0. So I have a situation where E naught equals mg h naught, and E1 equals 1/2 m v1 squared. So I start off with a whole lot of potential gravitational energy, and I end with pretty much no gravitational potential energy, but a whole lot of kinetic energy. Now you'll notice I didn't give a mass for the car, for the roller coaster car. Okay, well that might be a problem. Let's see though. We know that our initial energy is equal to our final energy by conservation. Again, what you start with, you end with. And so I'm going to do mg h naught equals 1/2 m v1 squared. Oh, well that's convenient. My masses drop out. I can multiply both sides by 2 to get rid of that 1/2. And I end up with 2 times g h naught equals v1 squared. I take the square root of both sides, and I end up with the square root of 2g h, my initial height, equals my final velocity. This is actually a nice general equation. This is one that applies in most circumstances as long as you're just dealing with potential energy and kinetic energy. So now I can plug things in. I know that square root of 2, 9.81 meters per second squared, times my initial height of 15 meters. Sorry about that. I plug those in, and I get my final velocity, which should come up to 17.2 meters per second. So I'd have meters times meter per second squared, so that's meters squared per second squared, and I take the square root, so that gives me meters per second. Yay, my units work out. 17.2 meters per second, so that's going to be roughly 35, somewhere between 35 and 40 miles per hour, I'd say. So it's moving pretty quick. But this is using conservation of energy to solve for that. And you can imagine this would be very difficult for us to solve using dynamics because we'd have to find all these different accelerations. Our acceleration changes based on where we are on this curve because our forces will point in all different directions. That'd be really unpleasant to try and keep track of. But luckily, because of energy, we can go through and we can solve it very quickly and very easily. That's the power of energy.